Okay, so I think we can start now. Let me make a friendly reminder that if you want to be notified about the class for any reason, you should send me an email so that I know that you're interested, okay? So I guess, let's see, last time, we essentially studied one formula, which is the Auslander book-bound formula. Auslander book-bound formula. Actually, before I get into that, let me also say that on my website, if you go to teaching, you can find the lecture notes for the course, and also you will find a link to a YouTube channel where you can find the recordings of the lectures. Okay, so then last time we were studying this formula that says the following. So if you have a local ring and you have a module of finite projective dimension, and this means that there exists a free resolution or a projective resolution of n that is finite, right? So this means something like this. Right? Then the following formula holds. The projective dimension of n plus its depth, equals the depth of R, right? And so this is the content of the previous lecture. This formula right here. And so remember, we also saw that the projected dimension of n has a conceptual interpretation like this. You're trying to find the maximal length, the minimal length of a projective resolution. And so this is also given by the maximum I, let's say this, I such that Tor of k comma n is non-zero, right? We also gave a name to this Tor, right? The I-vector number of n is the dimension as a k-vector space of this Tor module. And on the other hand, we saw that the depth also has a conceptual interpretation in terms of regular sequences, right? But on the other hand, it can be computed in the following way. It's going to be not the supremum, but the minimum of all the i's such that x of k comma n is not zero. Again, these two numbers have very nice conceptual interpretations. This one in terms of resolutions and this one in terms of regular sequences. But they can be computed by this formula, which is very useful. I'm sorry. You should have let me know that I need to note this. Okay, sorry about that. I hope you can see well. I was saying that these two numbers have very nice conceptual interpretations, but also you have these formulas that are very useful to prove things about them, right? And actually using these two formulas, we were able to prove this. The Alexander-Bookbaum formula. See, oops, right here, right? And so the reason why this hypothesis here is very important is that this formula can be proved by induction on this number, right? And so to do an induction on a number, you need that number to be finite, to be an actual number, right? Move the camera a little bit. So the other thing I mentioned the other day is that the depth of the ring is always less than the dimension of the ring. I added this as a little exercise on the notes in case you haven't seen this, but the reason is that a regular sequence can always be extended to a system of parameters of that local ring, and therefore you have this. And actually, here's a definition. We can say that R is Cohen-Macaulay if the depth of R equals its dimension. Lorena is here. So that's great. Okay, I'm just doing a little summary of the previous lecture, which is Alexander-Bookbaum. And I was writing down here the definition of Cohen-Macaulay, which is one of the most important notions in commutative algebra. Okay, and so you can see that what it means to be Cohen-Macaulay. So i.e. R is Cohen-Macaulay, let's say local, we are not talking about local Cohen-Macaulay rings, is Cohen-Macaulay if every system of parameters is a regular sequence. So regular sequences are like, they can always be extended to a system of parameter. But if you can go all the way up and find a regular sequence that is a system of parameter, then that's a Cohen-Macaulay ring. Let me move it like this. So the only source for system of parameters are regular sequences. So, well, actually, maybe I need to define this. I don't know if you have ever seen a definition of this. But this means like a system of parameter is a list of X dimension R elements. So here I'm saying that R has finite dimension, which is a consequence of this ring here being Euclidean. So it's a system of parameters if the radical of the ideal they generate is the maximal ideal. And they always exist. Okay. So that's a summary of the previous lecture. Okay. You can use my list, yeah. You can help me with that. So they always exist, and so yeah. Now we can move on to today's lecture. And so, yeah. So the whole point is that you can always generate the maximum ideal up to radical by dimension of R elements. But the catch here is that you have to use the radical. And so the next question is when you can generate the maximal ideal using exactly the dimension of R elements. Okay, so that's the content of today. So today we're going to start section 1.2, which is about regular local rings. Okay, can you move it a little bit? Actually, I can take care of it. I was doing that earlier, and I think it's fine. Don't worry about it, so I just need to get distracted. So, okay. Okay, thanks. Okay, so what is a regular local ring? So for this, we need the following definition, which is a definition of embedded dimension. So for this, take a Noetherian local ring. So I'm going to put parentheses here because we're going to follow the convention that all local rings are Noetherian. Just as a reminder. And so what I would like to, well, this is going to be the following. So this is going to be the minimal number of generators of n. And by Nakayama's lemma, there is a very precise way to compute that. So from last time, we were using this notation, mu of the maximal ideal. So mu of any module, of any finally generated module, is just the minimal number of generators. That's going to be given by the dimension as a k-vector space of k tensor that module. So you do a base change, you get a vector space, and you compute that dimension. That's going to be a finite number. And so, but often, instead of writing this tensor product, people write, you know, m modulo m squared because they are the same thing. Okay? So m modulo m squared is a k vector space, and the dimension is embedded dimension. Any questions so far? On Zoom, perhaps? Takes a little bit to react. Let's go all the way. Actually, we can go all the way here. So, fact, which is an exercise in the notes, but this is a consequence of Krull's ideals theorem. Okay. It says that the embedded dimension, just write that right here, is always at least the dimension of R. And actually, this is the reason why for Noetherian local rings, the dimension is a finite number because it is bounded by this. Okay, it's not true for arbitrary Noetherian rings, right? Because it may happen that at different points, you know, you have like the dimension goes up. There's a famous theorem of Nagata that illustrates that. Maybe I'm going to add it here to the notes whenever I have a chance. And so, definition of regular local ring. So, R is regular if and only if this happens to be an equality. the embedded dimension of R equals the dimension of R. And this makes sense actually, because this, if you know a little bit of algebraic geometry, you will see that this embedded dimension is supposed to represent the dimension of the cotangent space, or equivalently the tangent space at the point, right? So if you consider R as some affine variety, and you have a point, then the embedded dimension is the dimension of the tangent space. And so the dimension of the tangent space will be larger than the dimension around that point. And so if it goes up, it's because there is a singularity there, right? If these two things are equal, it means that your point can be approximated by a linear space of the same dimension. Okay, this is the intuition behind this definition and why it makes sense. Okay, so here is another characterization. Okay, actually, let me remark. I'm going to put it as a remark because it is an exercise that I hope you do. So I was telling you earlier how if a regular sequence, if every system of parameters is a regular sequence, then you are talking about a Kohima-Kohler ring. And now what we're going to try to see is that if the maximal ideal is generated by a regular sequence, then it is regular, right? That's the difference between regular and Kohima-Kohler. So this one is the exercise. If M is generated by a regular sequence, then R is regular. And again, this is a consequence of Krull's ideal. No, it's not called ideal. It's Krull's height theorem. I guess it should be the thing here. It's Krull's height theorem, right? Because that's the whole point of regular sequences, right? That they cut down dimension well, right? Like every time you cut out by an element, the dimension drops by one, right? And so if the maximum ideal is generated by a regular sequence, then you will see that the dimension of n modulo m squared has to be the dimension of R. Okay? So the regular sequences are designed so that happens. So they're extremely nice. You wish everything was a regular sequence. That's the point. However, the converse is true. And that's what we're going to prove. So, converse theorem, the converse is true. In fact, this is the following. So if you have a regular ring, it's a regular ring, it's regular, then every minimal set of generators of n, this also goes by the name of regular system of parameters. AKA regular system of parameters is necessarily a regular sequence. In other words, a local ring is regular if and only if the maximal ideal can be generated by a regular sequence. So it would be the perfect world if that's the case. Move a little bit. In particular, and this would follow, let's see, I think let's move a little bit more. In particular, let me have this here. The projected dimension of the residue field will be equal to the dimension of R. Remember, this was also the global dimension of the local ring. And so, remember that this number, actually, by the proof found also on the formula, is less than the depth and less than the dimension. So the depth is sandwiched between these two numbers. And therefore, the ring is Cohen-Macaulay. So R is Cohen-Macaulay. So actually, I was thinking, well, to give a proof of this, well, it would follow from what we have already and the Buchbauer standard formula out of this. But another classical proof is that if the maximal ideal is generated by a regular sequence, that means that the Kutzul complex out of that regular sequence will be a free resolution for K of length n. That's another way to get this. Let me move this a little bit more. Okay, any questions so far? As you may expect, the proof is gonna be an exercise because it follows from the following that I'm gonna write down and hopefully sketch a proof. We'll see. Okay. This is all rather classical. Everyone knew about this from a while ago. But there is a following, it's a consequence of the following. So, and by a consequence, that means it's an exercise for you to think about it, but it follows, right, from the following. And the it follows, right, let's put some quotes, because it's a meaningless thing to say, kind of. So, theorem. Irregular local ring is an integral domain. And this follows from two more lemmas that are very important, which follows from the following. So I need two lemmas. Well, I just need one of them. But I'm going to be using this lemma so much that I'm going to write it down here. This lemma is prime avoidance. And it is a general version that is not quite standard in commutative algebra textbooks, but it's the one we're going to be using all the time. So it says the following: suppose that you have an ideal that is contained in a finite union of ideals. Okay? So probably you know that if all of them are prime, it implies that A has to be contained in one of them. For some, right? If all of them are prime. However, we need the following version. So this holds if they are all prime, but two of them, or at most two of them. So we have the freedom of allowing at least two of them to be non-prime. Okay? If all but at most two of the AI are prime. Okay? And so the reason for this is actually you can just copy and paste the proof of the usual prime avoidance to prove this, and which is by induction on this number of ideals. But the point is that if there are exactly two ideals, this is just true. It's essentially a statement about abelian groups. So you can start induction there. Okay, the same argument by induction works, but the observation is that the inductive step is actually the statement about abelian groups. And so it works for any ideals, really. Okay, so but you can do the exact same proof. If you don't believe me, then you can try to prove it. Or I can give you a reference too. I just don't know a good one. See. Okay, well, I guess I can write the really important lemma in this little square here. So this lemma too is a consequence of this. And it says the following: suppose that you have a local ring whose dimension is not zero. So it's a positive dimensional local ring. Then R contains a regular element not in M squared. That's true for any regular local ring, as soon as it has some dimension. You can always find a regular element. Remember, that essentially means it's a non-zero divisor, that is not a unit, right? Sorry, that avoids M squared, not in M squared. Actually, this can also be sort of seen as part why the system of parameters always exists, because you have this. So you start with that element, you cook up the largest regular sequence you can, and then you extend to a system of parameters. Okay, so maybe The annoying thing is that now I have to go all the way back to the other board. I hope that's fine with you. All the way back here. Amazing. So why is lemma 2 a consequence of lemma 1? Right? So because to be a regular element, essentially, so a regular element let's say R, right, has two properties. It is in the maximal ideal, in other words, it's not a unit, and R is not a zero divisor, or in other words, it is a non-zero divisor, which means that it avoids all the minimal primes. Remember from your basic commutative algebra book or course that the union of the minimal primes of the ring is the set of zero divisors, right? The nilpotent ones are the intersection, and the zero divisors are the union. So to be a regular element, R has to avoid all minimal primes of R, right? And so a regular element is something that is in here, but avoids all minimal primes. So the claim actually we're making is that there exists R with these two properties, but it also avoids M squared. So the claim is that there exists R in M that avoids all minimal primes and it avoids M squared. Okay? And now you can use prime avoidance, right? Because another way to think about prime avoidance is that in order to avoid all these ideals, you have to avoid the union, right? And so the result follows if we can prove that M avoids the union. So that A avoids the union of the minimal primes. No, so I'm sorry. So the result would follow now make it well. I'm so sorry. So, well, it's sort of the equivalent thing, right? Like, so to be a non-zero divisor, you have to avoid the union, right? But like prime avoidance is equivalent to avoid all minimal primes. And so the claim is like to prove that such element R exists, we have to avoid all minimal primes, and we have to avoid M squared, right? So that's what I meant to say. I don't know if I made a little bit of a mess. And so the reason why M avoids all minimal primes is because of the dimension reason, right? If it's equal to one of the minimal primes, then the ring is zero dimensional. So M avoids all minimal primes because of dimension reason. It has positive dimension. That's the hypothesis. That's where you use it. And it avoids M squared also because of dimension reasons, because if M equals M squared, by Nakayama's lemma, M is zero, and therefore the ring is a field, right? So by dimension reason, you can avoid all of them, and therefore by prime avoidance, you can avoid the union, and you get like what you want. Okay. So I guess that's an exercise here too, but I kind of just solve it. Okay, so camera thing. Okay. Any questions so far? We're good. So, okay, so now with this we can prove of R is an integral domain. Let's say that R regular implies integral domain. Okay, let's prove this. Or let's keep a sketch of this. And I claim it's a consequence of the lemma on the existence of regular elements. So, okay, it's an induction on D equals the dimension of R. Let's do the case D equals 0. So, since I claim that a regular ring of dimension 0 is a field. Okay, because look, since R is regular of dimension 0, by definition you have that the dimension of R, which is 0, right, equals the dimension of K and n squared, right? That's the definition. But by Nakayama's lemma, that implies that n itself is 0. So it's a local ring whose maximal ideal is 0. That's a field, right? So this implies that R is a field, well, and in particular, an integral domain. Okay? And I claim that's the hard step of this proof because of the lemma, of course. Okay, let's go here. So now assume the ring has positive dimension, and all regular local rings of dimension less than t are integral domains. Okay, this is the inductive step. Look at this. Using the lemma, there exists R, there exists R in n, avoiding n squared. Notice that this is just another way to say that R is for sure part of a minimal set of generators of the maximum ideal, right? By Nakayama's lemma again. Where am I? Okay, move. And R is a non-zero divisor. It is a regular element. Okay? Let me make a few remarks of what this implies. Now, what we're going to do is to look at the quotient of R by little r. Let's look at the cool dimension of this ring. What do we know about this? Thanks to the fact that R is a regular element and Krull's height theorem. The dimension goes down by 1. That's what a regular element does for you. So the dimension of this ring is d minus 1. Okay? But this is also a local ring, right? A quotient of a local ring is a local ring. And what is the minimal number of generators? Let me move over here. But R modulo R is a local ring whose maximal ideal is generated by D minus 1 elements. Right? Because R is regular. So its maximal ideal M is generated by D elements. And R can be taken to be one of them by Nakayama's lemma. Therefore, if you would have a little R, you lose one generator. But you still have D minus 1 generators. Okay? It's a local ring whose maximal ideal, which is right, is just M modulo R. You know, like this idea is inside here, and you just kill R, right? Is generated by D minus 1 elements. In other words, it is a regular local ring of dimension D minus 1. That is, this is a regular local ring of dimension D minus 1. Therefore, we can apply the inductive hypothesis. Let me move here. I'm going to zoom out a little bit. So by induction, well, R modulo RR is an integral domain, but what does that say about R times R? It's a prime ideal. By induction, R times R is a prime ideal. Let me get my chart. It's a prime ideal, and it's not minimal. We started with this, right? R is a non-zero divisor, so it has to avoid all minimal primes. So it is not minimal. So let P be a minimal prime, right? It is not minimal, but it contains a minimal prime. Notice that we win if we prove that this P is 0. Because we will be proving that 0 is a prime ideal, which is what it means to be an integral domain. So this means that if we take X in P, you can write it as a multiple of R. There exists Y in R such that X equals Y times R. But R is not in P, so this forces Y to be in P, right? Because look, this product is in P, but R is not in P. So Y has to be in P because P is prime. But this means that P is actually equal to RP. And what do we conclude by Nakayama's lemma, given that R is in M? Look, P, the other way to think about it is that P equals M times P. the maximal ideal. And by Nakayamas, P is 0. Right? So there you are. It's very fun how everything is a consequence of Nakayama's lemma, right? You can define commutative algebra as the consequences of Nakayama's lemma. Okay, any questions so far with this proof? Or any question with any other thing? And believe it or not, that's the reason why the maximal ideal can be generated by a regular sequence. Let's go here. So, right, you see how the proof goes, right? So look at that, right? Like you start with R in R, a non-zero divisor, and then you model by that. And then you get a regular ring. And then that ring is an integral domain. And then you find a non-zero divisor and you model by that. And you go like that to find a regular sequence that generates M. Right? The whole point is that whenever you have regular M, you push it by that, it is regular. But it's also an integral domain, and so you continue like this. That's the proof, essentially, which I let you to write down properly. Actually, this thing has a corollary, which, well, it's actually very nice. So, corollary is the formation property of regular rings. Essentially, that's how you express this in fancy terms. So, suppose that you have a local ring, and suppose that you take R in n minus m squared, right? This is just another way to say that R is part of a minimal set of generators for the maximal ideal. It is in M, but it's not in M squared. So it's part of a basis of M modulo M squared, a K basis. Nakayama's lemma tells you that it is part of a minimal set of generators. So then, look at this. R is regular if and only if two things. Actually, we just proved one direction, and the other one is trivial. So, two things. First, R is regular. And two, R modulo R times R is regular. And I don't know how much time we'll have to this, but if we get we have a lot of time later, we can try to explore the properties of the F-singularities, like other F-singularities with this property. In general, given a singularity, you want to ask like when it deforms like this, the formation problem of a particular type of singularity. But for regular rings, it's sort of like immediate. Okay, so that's sort of all we need to know about regular rings. And now we are ready to express the most important theorem of this week. If you want, you can forget everything I said. All I need you is to remember the following theorem. Okay. Theorem. And this is a theorem with capital letters.
Javi, que R sea regular no implica ya que el cociente es regular.
Only if R is regular.
Okay.
Lorena is asking that if R being like regular implies automatically that R is regular. Okay. And no, so what it means is that, well, being a regular element means that it's an integral domain. Okay. That's what it means. But if R is regular, then you have that this quotient is regular. And that's actually this proof we had here. So yeah, theorem. And this is a theorem like, well, I thought it was a theorem of Serre, but looking at the literature is Auslander, Buchbaum, and Serre. Actually, you can look at the history of this theorem on the internet. And essentially what happened, if I remember correctly, is that Serre proved it first. I don't know, in the 60s, maybe late 50s, something like that. And a week later, like Auslander Buchbaum also proved it independently. But back in the day, like it was a different process, so it's sort of attributed to both of them. So they proved it together in one paper, but Serre had proved it first, like a week earlier, in French and whatnot. So, but it's the following absolutely magnificent theorem. Okay, take a local ring, an Noetherian, right? Noetherian local ring. Then the following statements, the following, I guess before write this, are equivalent. A, R is regular. In other words, according to what we just saw, N is generated by a regular sequence. B, R, let's put it like this, the global dimension of R, which remember is given by the projected dimension of K, the residue field, equal the dimension of R. In other words, R has global finite dimension, and it happens to be equal to it is its dimension, right? We proved that all local rings have this property. Okay. C. So in other words, we have already proved this. And well, C is just that this number is finite. The residue field has finite projected dimension. It's finite. In other words, suppose that you take the residue field and you start to construct a minimal free resolution. If you do that and you stop, then this is regular. So notice that this is equivalent to say that tor I kk is 0 for all I large enough. Right? I give you a minute, to appreciate this theorem if it is the first time you see it. Okay? It's an absolute masterpiece of mathematics. And actually, according to Serre, well, I think he wrote something like that in his paper. This is the right way to think about regularity. This should be the definition of a regular ring. Right? But what would happen if I tell you that the definition of a regular local ring is one in which tor of kk is 0 for I large enough, right? Like, who can understand what that even means? Any questions on Zoom? Maybe any comments? Maybe someone on Zoom has something nice to say about this theorem? Okay. So actually, notice that for this theorem to work, we need R to be local in the theorem. And so that is needed for this definition, at least in the theorem part. For this definition, we need finite dimension. There is no noetherianity to define this, right? Only that this dimension is finite. But for C, you can write that down, right? It's or well, you need local for this, I guess. But I guess okay, when you can write without using noetherianity at all, nor locality, is that this number is finite. So actually, you could say that, and some people do that, that an arbitrary ring, it doesn't have to be Noetherian, it doesn't have to be local, is regular if and only if it has finite global dimension. And that's actually Serge's definition of regular ring in general. I know there are still some debates going on, but I'm not so familiar with what are the debates, but it's very compelling to me that that's a good definition of regularity in absolute generality. Actually, that's what we're going to do in a second. So I'm getting ahead of myself. So no questions? Is everyone happy? Does everyone feel inspired by this theorem? So I think that if you see this theorem, you should just start to study commutative algebra and forget everything else because it's just so nice. Okay. Okay, so let's move on to the proof. How are we doing with time? I think we're pretty good. Just to emphasize, this theorem is the consequence of this week, right? All I wanted to say in the first week of classes is just this. This little thing here. Okay, so I wanted to do the proof in a lot of detail, but I'm just gonna do a little bit. It's just because this essentially follows from induction in a lemma, and I'm gonna leave the lemma as an exercise. So it's a good lemma. It's actually the deformation property of projected dimension, right? So lemma is an exercise. In the notes, this is exercise 1.15. So what you're going to do is that you're going to take a local ring and you're going to take a finally generated module and you're going to take little r in R that is a regular element on both R and M. In other words, it is a regular element on R, but also on M, right? So it doesn't kill anything of R, and it doesn't kill anything on M. And it avoids the maximal ideal. Okay? So with that in place, I want you to prove that the projected dimension of M modulo R, notice that this is an R modulo R module, right? It's a module over this ring, right? Because the action of R in here is 0. Therefore, it is well defined. So this is the projected dimension of M over R. So you can call this a deformation property of projected dimension of finally generated modules. So the proof is very nice. It's not too complicated once you know the trick. So well, where am I? So here in the notes, let me come back to myself. So here in the notes, I give you the hint and I break it down for you. Let me just say in words how it works. So the proof is essentially, so this boils down to the following. This boils down to proving that if you have a minimum free resolution for n, when you go modulo r, you have a minimum free resolution for mRn. What is the problem with that? You preserve freeness, but you don't preserve exactness, right? And to preserve exactness, you have to prove that certain Tor modules vanish, right? And so the vanishing of those Tor modules are obtained by this property where from these two properties, because what is the right way to think about these two conditions, right? Like, let me do it on a different color. Let me do it in purple. So this means here that you have two exact sequences, right? You have R modulo R multiplication by R. That's an exact sequence. That's what being a regular element means. And also for this. And so there would be a Tor module, right? That measures the obstruction to preserve exactness, and you have to prove that that Tor is 0. But then that Tor module is computed by these exact sequences. And since they are so short, the Tors you're looking for are 0. Okay, so that's how this works. I'll let you do the details. Now, why does this imply the Auslander-Bookman theorem? So let's do it over here. Proof of Auslander-Bookman server. Well, I only need to tell you why C implies A, right? So we want to prove that this is the hard part. If the projected dimension of the resistive field is finite, then R is regular. That's the good part here. So what do you think? We're going to do induction, right? Because we want to apply this property here. So this property cries induction, right? Induction on D, which we're going to call the dimension of R. And I claim that because of this lemma, the only hard step is D equals 0. If D equals 0, right? What does the Auslander-Bookman formula says? What does it say about the projective dimension? So since this is finite, we can apply the Auslander-Bookman formula, right? That's the hypothesis of it. And so it's going to imply that the projected dimension of K is 0, right? Because it is bounded by the depth, which is bounded by the dimension is 0. So this is 0. And what does that imply about K? That K is projective, but it is finitely generated, so it is free. So K is free. It's an R module. What does that imply? K has intorsion, right? So it forces the maximum ideal to be 0. Is a field. And fields are regular. The maximum ideal is 0, so it's generated by the 0 element, which is the dimension. Right? The 0 ideal is generated by empty, as I said, right? So it's generated by 0 elements. So that's why fields are regular, I suppose. Okay, any question with that step? No? And so let's look at the inductive step. Move the camera. Okay. So actually we're going to apply, well, I erased the lemma that was in this little blackboard, right? Because now we're going to assume positive dimension. And then I'm going to cook up a regular element. Okay, so inductive step, right? So this means that I can assume that the dimension is positive, and therefore I can cook up a regular element that, you know, avoids m squared, right? So so by the lemma, which is essentially prime avoidance, we can find there exists a regular element that is part of a minimal set of generators of the maximal ideal. Regular element. Right? And so it suffices to prove that by the deformation property of regularity, that R modulo R is regular. Well, this has the following maximal ideal. And what is the residue field? What is this? What is R? Well, what is this modulo this? It's R modulo M, which is just K. So they have the same residue field. Is regular. But to prove that, by the inductive hypothesis, it suffices to prove that the projected dimension of this is finite in here. So it suffices by induction to prove that the projected dimension of K as an R modulo RR, sorry, as a modulo over this ring is finite. And now you apply the lemma. Because this is the projected dimension of K over R. Because K modulo R is just K. Because R is 0 on K. Right, like, sorry, K modulo R times K is just K modulo 0. Because R is in M, so it is 0 in K. Right? By the lemma. And there you are. That's the proof. The proof is that projected dimension deforms well, and then you can do induction, and the step 0 is just L-standard with formula. Any questions? Are we good? Okay, that's awesome. They were killing it. We should be proud of ourselves. And we have 5 more minutes. Actually, I apologize because last time I went to 12:30. I thought the lecture was supposed to be 1 hour and a half, but it's 1 hour and 20 minutes. which is already a lot. So I'm sure that you're tired, you want to go home, so I'm just gonna end up with a few remarks. So now we can define what a regular ring is. I can do that in a few minutes. So thanks to this, the following definition makes sense. So definition. Take R a Noetherian, finite dimensional. Remember, like Noetherian only implies finite dimension in the local case. So I'm going to take a Noetherian finite dimensional ring is regular if any, and therefore all, of the following equivalent conditions hold. So first, well, let's say A. RP is a regular local ring for all P in the spectrum of R. 2. The global dimension of R I guess you can say it's equal to the dimension of R. No, it's bounded because yeah, let's put it bounded. And C, R has finite global dimension. And what I was saying earlier is that these two conditions here require these two hypotheses for them to make sense. However, C doesn't require that. So if you want to drop these two hypotheses, you can say the definition of regular is C. But I think that could be still up to debate if that's a good definition or not. I don't know. I'm not so sure. I'm not involved in those debates at all. So. And I'm going to leave you as an exercise to prove that these things are equivalent. Okay. And this is going to be the definition of regular ring. And that's all I wanted to tell you, how you define that properly.
Is for any Noetherian ring?
Yeah, R has to be Noetherian and finite dimensional.
Not necessarily local.
Not necessarily what? Local.
Local.
Yeah, it doesn't have to be local. So, but they do coincide, right? Like we had the definition for the local case, and this is how you extend it.
Okay.
But what this does to you is that it tells that these two conditions agree. So and therefore this is a good definition. Actually, the whole point of this characterization was to prove that the localizations of local rings are local. That was far from trivial. So so to prove that these are equivalent, you're going to have to do all we have seen so far. I'm going to leave it as an exercise. We are almost there. I think what time is it? Can you remember the time? It's 1:20? It's almost 1:20. So so I guess so the only section we are missing for today is a section about complete local rings and the structure and the coherent structure theorems. That's going to be a black box in this course, like how the coherent structure theorems. So I'm going to let you read them in the notes. Maybe next time I'm going to go super fast on that. But on next week, the idea is to start with the Kunz's theorem. We're going to prove Kunz's theorem next time, and that's the goal. So for that, we're going to use the coherent structure theorems. But please just read them here in the notes. It's section 1.4. So that's for you to read at home. It's just a reminder of what they are. And we won't prove them. It's just a black box for us. And so yeah, let's stop here. And if you have any question, we can do that now. Or any questions? Okay, so also remember that there will be virtual office hours today at 2 p.m. And so if there are no more questions, see you next week. Thank you.